Hi, myself Debaparna Sengupta, Assistant Professor, Electrical Engineering Department, TICT, Rajarhat, Kolkata. My today's topic of discussion is losses in a transformer. So before starting the session, I just want to convey the learning objectives of this lecture. After watching this video, students will be able to: number 1, define and explain copper loss and full load copper loss of a transformer and explain their relationship and calculate it. Point number 2, define and explain hysteresis loss of a transformer and explain the process of reducing it and also calculate it. Number 3, define and explain eddy current loss of a transformer and explain the process of reducing it and also to calculate it. Before starting the main session, I just want to discuss about the prerequisites for this session. So before starting the session or before listening the lecture, what is expected from the students? That means the students must know the construction, working principle, EMF equation, no load and on load operation, phasor diagram and equivalent circuit of a transformer. Let's start with copper loss. What is copper loss? What is the expression for copper loss? And finally, how can it be minimized? So what is copper loss? As the name indicates, copper loss is naturally the loss inside the copper. That means the winding, because the winding is made of copper. So we can say copper loss is basically the energy loss in the copper windings of a transformer, and this loss is dissipated as heat from the windings of a transformer. And what is the expression of copper loss? So before knowing the expression of copper loss, you must know about the equivalent resistance of the transformer circuit. That means the resistance referred to the primary or the resistance, total resistance referred to the secondary, or maybe separately R1 and R2. That means resistance of the primary and resistance of the secondary. The resistance of the primary winding is denoted by R1 and resistance of the secondary winding is denoted by R2. And I1 and I2 are the primary current and secondary current. So the total copper loss is equal to the primary copper loss plus the secondary copper loss. So primary copper loss is obviously I1 square R1, as I1 current, that means primary current, is flowing through R1, that means primary resistance, and I2 current is flowing through the secondary resistance R2. So the copper loss in the secondary side will be I2 square R2. Therefore, the complete expression of the copper loss, total copper loss, will be I1 square R1 plus I2 square R2. In this expression, we have not shifted the parameters of the secondary to the primary or the parameters of primary to the secondary. That means we have not utilized the equivalent circuit referred to the primary or referred to the secondary. If we can find out the total resistance referred to the primary, that means R01, then in terms of R01, we can write the total copper loss is I1 square R01. If we convert or we can shift all the parameters of the primary side into the secondary side, and we are able to find out the R02, that means total equivalent resistance referred to the secondary. Then also I can get the total copper loss by the expression I2 square R02. So this summation of I1 square R1 and I2 square R2 is equal to I1 square R01, and this is once again equal to I2 square R02. So these are the three equivalent expressions by which we can calculate the total copper loss of a transformer. And what is the process of minimization of the copper loss? The process is very simple. We have to somehow reduce the values of R1 and R2. That means the primary winding resistance and the secondary winding resistance. As all of us know, R equal to rho L by A. Rho is the resistivity of the material, and L is the length of the conducting material, and A is the cross-sectional area of the conducting material. So if we somehow can reduce the value of R, that means resistance of the conductor, then we can get a control over the copper loss. Okay, so this can be done by either reducing the length of the copper or increasing the cross-sectional area of the copper conductor. So if I increase the cross-sectional area of the copper conductors, that means if we use thick conductors, then automatically our cross-sectional area will be increased and R will be decreasing. As the R will be decreasing, that means R1, R2 both will be decreasing. So the total copper loss will decrease. So that this is all about the copper loss. Next we will move on to the iron loss. As the name depicts, iron loss means the loss inside the iron. Iron means the core, because the core is made of iron. Iron loss can be classified into two types of losses. One is the hysteresis loss and the second one is eddy current loss. So what is hysteresis loss? What is the expression for hysteresis loss and how can it be minimized? Hysteresis loss is one kind of energy loss inside the core of a transformer, and this energy is required for the compensation of residual magnetism of the ferromagnetic core of a transformer. As the core is made of magnetic material and the supply voltage is AC supply voltage, that means constant reversal of magnitude and direction is going on inside the winding, and the flux is also fluctuating in nature. That's why there will be constant magnetization and demagnetization of the core. As the core is made of ferromagnetic material, there will be some residual magnetism trapped inside the magnetic material. That means the total energy will not come back to the source. Some energy will remain inside the core in trapped condition, and that is called the hysteresis loss. So the loss of energy due to residual magnetism is termed as hysteresis loss. And what is the expression? The expression of hysteresis loss is pH equal to KH multiplied by Bm to the power n into F into V. Here KH is called the hysteresis coefficient, Bm is the maximum flux density, n is another constant which is also dependent on the magnetic material, and this F is the frequency of the supply voltage and V is the volume of the core. So if we have taken decision at the designing part about the volume, So we cannot change that volume, and frequency of the supply is constant, as we are in power system we are actually using a constant voltage supply of constant frequency, and this BM value, maximum flux density, this is also dependent on the magnitude of the voltage. So whenever I am supplying a voltage into the transformer, usually this is of constant voltage magnitude and constant frequency. So my BM value and F value should be taken as constant, and KH and N, these are the constant which is dependent on the selection of magnetic material, and V is the volume of the core. So this is ultimately the expression of the hysteresis loss. So now move on to the process of minimization of this loss. As I have already told you, this BM and F, these things are actually dependent on the supply voltage, magnitude and frequency, and that has been taken as constants, and V is also a constant. So we can only change this KH and N. That means those quantities are totally dependent on the magnetic material used. So by carefully selecting a suitable type of magnetic material of low hysteresis coefficient and low value of N, we can easily reduce the hysteresis loss. The next topic, or you can say subtopic of discussion, is eddy current loss. What is eddy current loss? What is the expression of eddy current loss, and how can it be minimized? Eddy current loss is one kind of energy loss inside the core of a transformer due to the EMF induced inside the magnetic material of for its conducting property, and circulating eddy current flowing inside the core of a transformer. Eddy current is basically due to the conductive nature of the magnetic material. The magnetic material is not only a magnetic material, it will have some conducting property also, as it is made of iron, and it will also cut some flux, and according to the Faraday's law of electromagnetic induction, a voltage will be induced inside the core also, apart from the windings, copper windings. So due to that induced voltage inside the core, a current will be circulating inside the core, and that current is called eddy current, and the loss due to eddy current is called eddy current loss, and this can be expressed by I square Re also. What is I square Re? I is the eddy current flowing or circulating inside the core, and Re is the resistance of the core. Another expression of eddy current loss, which is extensively used, is P equal to Ke Bm square F square T square V. P is the eddy current loss, Ke is the eddy current loss coefficient, Bm is maximum flux density, F is the frequency, T is the thickness of lamination, and V is finally the volume of the core. So as I already discussed, for reducing the hysteresis loss, we have already selected the material, and the volume of the core is also pre-decided. So we cannot change this V, and BM and F, these are dependent on the magnitude and frequency of the supply voltage. We cannot change all those things. Okay, so we can only change this T. Ke also cannot be changed because it is also dependent on the magnetic material, and we have already selected the magnetic material. So the one and only way for reducing the eddy current loss is to reduce this T, that means the thickness of the lamination. If we use a solid core, then there will be no T. T value is actually I can